Hello everyone, my name is Feiyang Fiona Jiang, and today I will be explaining the Big O notation through the example of two very common searching algorithms, linear search and binary search. So what is the Big O notation firstly? It is a commonly recognized way of measuring the efficiency of an algorithm in a theoretical way. So instead of measuring the actual runtime that it takes for an algorithm to run on the computer, which is very relative and depends on the quality of the PC you have, this is actually the fairest way to measure the efficiency of a program based on the theoretical runtime that it would take. So let's look into the example. Let's start with a linear search. So as most of you would probably expect, the runtime of the linear search is just linear runtime. That is big O of n. And what it means is that as the n, which is the size of the array, expand, the runtime we would expect to get to the search would scale by the same amount. So for example, this here is a for loop, and it loops through every element from 0 to n, which is the size of an array. And every time it compares with the current item, this is a constant time operation, but this constant time operation gets executed n time, which gives us a total runtime of n. And this is actually because we increment only by a size of 1 every time, and that is very inefficient. Why? Let's look through this example. So for example, let's say we double the size of the array by the same amount. So right now it has 9 elements here. Let's say we add another 9 here. So what if the item we're trying to search is a worst case scenario at the very end of this array? How much more time do we need to increment in order to get into that new target? This will be 9 times, right? Because we will search every element in this list as well until we get to the target. So that one means the time we search goes from 9 to 18, which basically is multiplied by 2. And looking back at the size of our array, it becomes 2n as well. So it increased by the same factor here. So that's why we're calling it linear, because as the array scales, it scales by the same amount. However, things played a little differently for this binary search. Let's look at the code here. Well, at first glance, you might think that it's probably very similar to linear search because, well, it has this while loop here. However, the thing you should notice is not they have the loop. However, you should notice like how much they increment every time within the loop. What is the size of the increment? So this line becomes very important here because it shows that every time when you do a comparison, you did not just eliminate one item, you eliminate half of the remaining item. And this becomes key. So let's say the item we're trying to search is actually, let's say 47. And in this way, because you're trying to find the middle element every time, and in this situation, let's say for this element as example, and then I compare with 47, it's smaller than 47. It rule out half of the array instantly. And then this pattern goes on. So we probably can reach 47, our target, within 3 to 4 times of comparison. And let's say we double the size of this array as well. We added another 9 elements here, and then we're still trying to search for 47. How much would it increment the number of time we will compare? It wouldn't be incrementing 9 times as we have with linear search, right? Because let's see, if the first time I find the middle element, it's either like 53 or the item right next to 53. If we're searching 47, it gets eliminate this half immediately. And then we're back into this pattern again. So at the very most, we're incremented by 1 time. And you see, this is the power of this binary search. And what is the runtime of it? Because every time we eliminate half of the array, so we're trying to actually find this x here in which is how many time of the n elements that we have, so we can divide it by the size of 2. And then that is basically just this x here, right? So if you do the math and calculate, try to solve for x, you will realize that x is equal to log base 2 of n, which basically simplifies into big O notation of log of n. And you can see how significant this is if you compare to how they look on the graphing calculator. So see that they started off very similar. However, as you scale the size of this array input, you will see that their difference gets larger and larger. And this is just the difference between the log n and linear runtime. There are actually algorithms exist that with much worse runtime. For example, there are algorithms that contains quadratic or exponential or even factorial runtime. So you see how this difference is getting larger and larger here. So that's why we need to really write very good program and try to avoid very high big O runtime. So that's it about a little lecture on the big O notation, and I hope you enjoy. Thank you.